Here's a better example that's not so sketchy. We have the function x squared minus 2x plus 2 graphed here, and it's going to be a specified interval that we're looking at. Whoops. So the specified interval is going to be this right here. So notice it is a closed interval, and because they're only saying consider this interval of our function, I'm going to close everything else off, because all I'm interested in is the values between 0 and 3 on the x line. So there it is. Alright, and once again it is closed, so those squared brackets indicate that. So we are including that x equals 0 and that x equals 3 point. There is a defined endpoint there. So if I were to ask you, what are the extrema? Well, I should ask, what is the absolute extrema? Well, once again, we're looking for the point that's greater than all other points. So what x value has a point that's greater than, has an output that's greater than all other points? And I think you can go ahead and say, well, here is the maximum right there. At x equals, and then I can go ahead, exactly our endpoint, 3. At x equals 3, this is going to have a y value that's greater than all others. So you can actually specify that point. It's going to be 3 comma by going ahead and plugging it into our equation. 3 squared minus 2 times 3 plus 2. So what do we got there? We have 9 minus 6 plus 2 is 5. And you can kind of see that visually too on the graph. Now if I were to ask you also for any other extrema, well yeah, there is a point at x equals 1 right here where that is going to produce a y value that is less than all other y values. You can see that at x equals 1 we have a minimum. Oops, sorry, messy. Okay, and once again, you could actually, you can look at it on the graph-wise. Otherwise, you can plug that in to see what that actual point is. 1 comma, and then we have 1 squared minus 2 plus 2. So what we have there is 1. So those right there are absolute extrema. I also want to point to one of the theorems of this chapter, and it's the extreme value theorem. And all it really says is, as long as it's continuous over a closed interval, and I emphasize the closed interval, then we know that there's going to be a minimum or maximum on it. There's really no way around it. We can go back to this equation this example right here. Those endpoints, having the fact that it's an endpoint, means that we can just define at this very point it's going to be higher or lower. Okay. I do want to say you could have an example or a case like this where, let's say, we're just looking at it from the window of -2 to 2. So that interval right there. So I'm going to close it off. Whoops, I missed my mark again. We're going to close it off there. Okay, so I could have something that looks like this, and what you'll notice is those maximum and minimum points might not happen at the endpoints, but because it's continuous, there has to be something going on in between where, yeah, you do achieve that maximum and minimum. So also to consider why there's emphasis on the fact that it's a closed interval. Consider the interval that's open from 0 to 3. So once again, I'll close this off. You could go ahead and say, yeah, well, here's my maximum right there. But what is that? What x value is that? Because this is open, someone could go ahead and say, well, yeah, the maximum happens at 2.9. But then someone else can always top that and say, no, it's 2.99 at x equals 2.99. And someone can always, of course, top that. So is there any value that's greater than all the others? No, there is no y value that I can name that's greater than all the other values, because I can always choose the next value closer and closer to that 3. Yes, there is an absolute minimum. It's located right here. but I can't say that there is any maximum. So just looking back, the extreme value theorem, as long as it's closed, you know that it's going to have some sort of minimum or maximum in there. You can't always say that with an open interval. Alright, so we've talked about absolute now. The absolute was when there is some sort of point on the graph such that that y value is greater than all the others, or if we're talking a minimum, then there's some sort of point on that graph such that the y value is less than all the others. But now let's look at this graph. If you'll notice, this is an open graph, you could call it, because there is no endpoints to it. It's just continuing off the charts. So I could widen the screen, but the point of this is to say that I do have these relatively high and low points, and those are what we call relative extrema. And basically, that is the peaks of the hills and the lowest points of the valley. And also, I should have said high or low endpoints. Those are also included. But once again, you're going to have endpoints in order to state endpoints. So now you're probably asking me, what does all of this have to do with derivatives? Why did we spend an entire chapter on doing derivatives? Well, I do want to show you why. This is a program that just kind of lets you graph any kind of function and then observe tangent lines, normal lines. I don't even know what these other ones are. But if you kind of follow this pink line as I trace it along this function. So this is a sine function, by the way. I just want you to kind of observe this tangent line. So right now it's getting pretty steep, a negative steep rate of change. Alright, now it's going to start to get less steep, less of an incline. And as I reach this relative minimum, you'll notice that it's going to flatline. Alright, and then as I trace this up some more, I'm reaching an absolute or a relative maximum, a peak of a hill. Ah! Another flat line. And then you can kind of just see as this rate of change right here, once again as we do a valley, that rate of change, 0. It's 0 rate of change. So, alright, so how this has to do with derivatives is what we have are what we call critical numbers, and the critical numbers are values of x for which the derivative f prime of x is equal to 0 or is undefined. So in that example where you saw that pink line, flat line, what you notice, those slopes, the slope of those tangent lines, so in other words the derivatives, at those instances they were equal at 0.